トン先生、Professor Thomas Hinton、福島大学、またコロラドステートユニバーシティにも所属していらっしゃいます。トーマス・ヒントン先生は1989年コロラド州立大学にて放射線生態学の博士号を取得されております。その後、スイスのポールシェラー研究所、それからアメリカジョージア大学サバナリバ生態研究所、フランス放射線防護原子力安全研究所を経て、現在は福島大学、それからコロラド州立大学にてご活躍されております。ご専門は水生および陸生生態系における放射線汚染物質を調査されていることです。放射能汚染された生態系の修復、それから汚染物質の挙動のモデリングを中心に現在ご研究されています。数多くの論文を執筆され、2010年には放射線生態学者としては初めてウラジミール・シェフチェンコ賞を受賞されております。それでは先生にご講演いただきますが、タイトルはすみません、Environmental Effects of Operating the Savannah River Site and Nuclear Production Facility ということで、すみません、タイトルも通訳していただいているんですがね、サバナリバー核施設からの放射線漏洩と生態系環境影響ということでお願いします。
Thank you, Arya-san. Thank you, Honda Sensei, for the kind invitation. Let's see, Oh, okay. Thank you very much.
You're welcome.
Okay. So I'm going to give you an overview of the Savannah River Site over a period of about 50 years. I'm stopping at this point for reasons I hope will become apparent during the course of the talk. Basically, most of the radionuclides stopped during that period, so the releases have been minor since then. The Savannah River Site is located in the United States in South Carolina. South Carolina and Georgia are borders, and there's a river that runs between them called the Savannah River. The site was started in about 1950. The Savannah River Site is a nuclear production facility. Their primary products were tritium and plutonium-239. Are we okay with the microphone? No. Testing? 1, 2, 3. Is that better? Yes. Yep. So they produce tritium and plutonium. This is out of the Columbia newspaper in 1950. It's saying giant atomic project to rise near Aiken. Aiken was another city close by. We'll make H-bomb materials. 1,500 families must move from this area of 25 square miles in order for the government to come in and produce these facilities. So let me remind you of how plutonium is made. They use uranium-238 as a target in these reactors. They bombard it with neutrons. A neutron is absorbed within the uranium-238. That becomes uranium-239. Through beta decay, it becomes neptunium-239. Another emission, beta decay, and you end up with plutonium-239. This is the product that they were interested in. The other product they were interested in is tritium, and that's made from neutron activation of lithium-6. Let me also remind you about the nuclear fuel cycle and many of the facilities involved, because many of these facilities are on the Savannah River Site, and I will be talking about them, and this will help you perhaps follow a little bit. So uranium is mined and made into a gas, uranium hexafluoride. It's then enriched. Natural uranium is largely uranium-238. The product that they're interested in is uranium-235. 235 is fissionable, uranium-238 is not. 235 occurs at a natural abundance of less than 1%. They would like to enrich it to a higher percentage. So there's this enrichment facility. Once uranium-235 is enriched, and it's enriched generally for maybe 3% for nuclear power reactors that produce electricity, it might be enriched to, say, 90% for nuclear reactors in submarines or for weapons production. Once it's enriched, the uranium-235 is made into fuel rods, or the uranium-238 is made into target rods, in which they will bombard these target rods with neutrons. This material is then put into a nuclear reactor. If it's a commercial nuclear reactor, power is generated. This basically just boils water, turns a turbine, and power is produced. This did not occur at the Savannah River Site. No electrical generation was made from any of the reactors on the Savannah River Site. Their purpose was to produce these products that I already mentioned. Once the fuel and target rods are spent, and they've served their purpose, they are moved into a temporary storage area. This is like a big swimming pool. Glides to decay. This is an important source of radionuclide. If rods have been stored sufficiently long, they are taken to a reprocessing facility. And there, it's a big, huge chemical process at an industrial scale to chemically extract the products that they're interested in. Then the waste is taken care of, or products are shipped different places for different reasons. So this is the Savannah River Site. This is South Carolina, and this is the Savannah River, and this would be Georgia. On the Savannah River Site, there was a fuel and target fabrication facility. There were 2 chemical reprocessing facilities. There was a deuterium facility. I'll talk about that in a minute. And there were 5 nuclear reactors, as well as a waste management area. Notice that each one of these reactors is located on a river. These rivers were used for cooling purposes, and the discharges from these reactors went down each of these rivers into a large swamp complex adjacent to the Savannah River, and then into the Savannah River, eventually into the ocean, I'm guessing 150 kilometers downstream. So I'm going to talk about all of these different facilities. I'll tell you a little bit about the releases, radioactive releases. I'll tell you a little bit about the dose to humans from these releases, and then I'll talk a little bit about the environmental impacts from these releases. In addition to the radioactive releases, I'll talk about the thermal discharges, hot water, and I'll talk about changes in land use. Without doubt, there were environmental impacts. This is a photograph of a nuclear reactor in the background, taken probably in the 70s, and the effluent is coming downstream. These are dead trees and damage to the environment. The question is, what caused it? And hopefully I'll be able to answer that for you here in the next few minutes. So a bit of history here. The facilities operated from about 1953, this is a mistake, until 1988. These are the 5 reactors. They were coded by letters, RPK. There were 2 chemical separation facilities, again coded by letters, F and H, and you'll see these in subsequent slides. So basically, things were very active from 1953 till late 1980s. I mentioned heavy water. Heavy water was used as the primary coolant and moderator in the nuclear reactors. Heavy water is just a water molecule with an extra neutron. So you get this rather than this. Heavy water occurs naturally at a very low percentage. And there was a facility on the Savannah River Site that took water from the river and enriched it to obtain deuterium for the nuclear reactors. Fuel rods were fabricated on the Savannah River Site. The enrichment of U-235 occurred in Oak Ridge, Tennessee, another facility. The enriched uranium was sent to the Savannah River Site, where it was made into pellets and into fuel rods that then went into the nuclear reactors. This target rod facility ended up being the largest source for uranium releases. The peak uranium release occurred in about 1969, 11,000 kilograms of it, 0.3 terabecquerels. There were also waste storage facilities on the Savannah River Site. This is a photograph of how they deal with low-level waste. This would be contaminated gloves, contaminated clothing, etc. They would go into these big boxes, and this is a pit that's been dug into the earth. After the pit is lined with all these boxes, then they would cover it back up with dirt. About 90% of the low-level waste has half-lives less than 50 years, and this is the total activity as of the late 1990s. There are over 150 waste areas on the Savannah River Site, and these are the volumes for low-level and mixed. There was also high-level waste, and there were 30 double-shelled underground tanks, very large tanks, 4 million liter capacity with this amount of radioactivity. So the high-level waste is stored there and then taken out, and there's a glass vitrification process to make that waste more stable. Also on the site there were several seepage basins. Here's a photograph that depicts 3 of them. Short-term waste was put into these seepage basins. Several of them were lined with plastic to prevent the waste from going down into the soil, but many of them were not lined, and they were a source of groundwater contamination. This one here has been remediated. This is a photograph that shows the tops of those big barrels, big tanks that I showed in the previous photo. So here's a photograph of one of the 5 nuclear reactors. The reactors, as I mentioned, operated from the early 50s until 1988. This is a depiction of the power outage for all of the reactors and when they operated. So the first reactor to come online was our reactor in about 1955, but it only ran until 1964, and then it was taken offline. I'm going to be concentrating on L reactor a bit later in my talk, and it's important to note that it ran until 1969, was shut down, and did not come back online until 85, operated for 3 years and quit. The maximum period of reactor output occurred in the early 1960s. Each reactor had one of these facilities for storing spent fuel and irradiated targets. As I mentioned, these are like big swimming pools where these rods are kept. Each one is about 10 million liters. They're stored here for about 9 months. The water in here during the early operational periods, 1970s, was routinely discharged into streams with no treatment. The fuel rods that were put in here often had tiny cracks in the outer casing, so the radionuclides that were inside would leak out and contaminate the water, and then it would be discharged into the stream. So this was a major source of radionuclide release from the reactors. This is a photograph of a fuel rod that's cracked. This is Parr Pond, and in 1957 there was a significant release of radionuclides from one of these failed fuel rods. Okay, so now I'll just go over some of the releases over time and tell you a little bit about the different facilities and the types of releases that occurred. Overall, the reactors released large amounts of tritium and argon-41 into the atmosphere. This is the lower graph is from 1955 to 1991. The line represents the separations facility. That's where they chemically separate the product that they're interested in. And the bars represent the releases from the nuclear reactors. So you can see that the separations facility was the primary source for much of the tritium releases. This is a photograph of one of the chemical separation facilities when it was being built. It was, as I just mentioned, the largest source for tritium releases into the atmosphere. So here's the total releases from the Savannah River Site. I'll show this to you by pathway, atmospheric stream versus seepage basins. These are the total releases from 1954 to 1988 from atmosphere. And you can see that tritium, krypton, and argon dominated. This is e to the 5th, e to the 6th terabecquerels over this entire period. For stream releases, again probably from the reactors, the distribution of the radionuclides differs a little bit, as well as the total amounts, with chromium being important, as well as cesium-137. We'll talk about that in a moment. The seepage basins that I showed you photographs, that's depicted here by the white bars. Again, a suite of radionuclides were put into these seepage basins, with some of them leaking into the groundwater. Let's see, in 2000, the government agency Center for Disease Control and Prevention conducted a major study of doses to the people living around the Savannah River Site during its first 50 years of operation. And they hired a prime contractor called Risk Assessment Corporation. And RAC did a complete source term evaluation of all releases from the Savannah River Site from all of its facilities. An extremely thorough job. And it's this data set that I will be showing you, and it's in part why I ended the analysis in about 2001, because there has been little additional work since then. So these are data from RAC. This is a screening level human dose assessment. It asks the question, what radionuclides contributed most to the public's dose? And it's looking at two pathways, airborne in the top graph and aquatic in the lower graph. This is percent contribution, and it's 1%, 10%, and 100%. So you can see from an airborne perspective the radionuclides that contributed most to the public's dose was tritium and iodine-131. These are the same type of figure for aquatic releases, and you can see at the 10% level you have strontium 89 and 90, but without doubt cesium-137 was the dominant radionuclide contributing to the public dose from the aquatic releases perspective. These are the dose to a hypothetically maximally exposed individual that resides next to the Savannah River Site from 1954 to 1996. And it's two different pathways, aquatic and atmospheric. And you can see that from the aquatic perspective, it's these radionuclides, phosphorus, zinc, strontium, also cesium-137. From the atmospheric perspective, argon, tritium, plutonium. This is a combination of those two pathways from 1954 to 1966. It's the population dose, and it's the percent of the total dose. And you can see that tritium contributed most, followed by zinc and iodine and other ones, with cesium being here and the other radionuclides decreasing. The dose for the public was about 5 person sieverts. Person sieverts is kind of a strange unit. What that means is that you add up the dose to all the individuals. So for example here, this individual got 0.1 sievert, this one 0.4, etc. And in this example, the person sieverts would be 0.75. These calculations indicate that the person sieverts was about 5. Okay, so that ends that first part, which was basically what was the dose to humans. And it's 5 person sieverts or so. No single individual got appreciably huge doses from all those releases. Now I'm going to change a little bit and talk about the environmental doses. But that analysis is so complex over so many years and so many radionuclides that what I've tried to do is target the worst case situation and the worst facility that released the most radionuclides. So here we have all the different facilities, the seepage basins, the F and H separation facilities, the reactor seepage basins, and the reactors themselves. These bars represent the percent of total activity released for the fission products and for tritium. And what you can see is that the reactors by far released the most radionuclides compared to all these other facilities. So now to do this environmental impact analysis that we're going to walk through, I'm just going to concentrate on the reactors areas because that's the worst case situation. Because the reactor areas were releasing largely to streams, we'll look at the various streams that came from the nuclear reactors, and we can see that this stream here, Steel Creek, received the greatest releases. This is cesium-137. This is 1952 to 1978. Sorry, these units are in picocuries per liter, which are a very archaic unit used in the United States. 100 picocuries is about 4 becquerels. So what I want to do here is show you that Steel Creek is the most contaminated. So now the rest of my talk will concentrate on the environmental impacts to Steel Creek, and we'll ignore these others for simplicity's sake. Here's the concentrations of radionuclides in Steel Creek. These came from L reactor, and remember that slide where I showed you that L reactor stopped operating for a period of time. That's why there's this break in the releases. This is 1955 to 1985, the entire period that L reactor was operational. This is becquerels per liter, 10 to the second, 10 to the fourth. This shows that tritium was the radionuclide with the highest concentrations released into Still Creek, with all these other radionuclides, cobalt, zinc, strontium, cesium, being 1 to 100 becquerels per liter. Okay, now we're going to take those data and we're going to do a rough risk analysis. And the way I've done this is to use the Department of Energy's biota dose assessment model. That model uses a tiered approach. They take a very simple approach where they try to make a worst case scenario and screen out radionuclides that fall below some critical level. That critical level is the IAEA guideline of 1 or 10 milligrays per day. I'll show you that in a minute. So what we're going to do, what DOE has done, is they've back calculated the environmental concentration that would give the environment a 10 milligray per day dose. For example, say, in order for a fish to get 10 milligrays per day of cesium, the concentration in the water would have to be 100 becquerels per liter. So now I can look at the concentrations in my river, compare it to the 100 becquerels per liter, and make a rough estimate of what the environmental impact was. I'm waiting for my interpreters who are doing an awesome job. These calculations consider both internal and external pathways. These are the DOE bioconcentration guides that I mentioned. This is becquerels per liter. So for cesium, it wasn't 100, as I mentioned. It was 40 for fish, but it is 2 for riparian. Riparian means associated with rivers. So it would be animals who are spending a lot of time in the river, who might be eating shellfish or fish or wading in the water. And the typical example there is raccoon. Because it's a mammal, it's more sensitive than fish. So therefore, I'm going to concentrate the next few moments on the mammals and the riparian pathway, because that's the worst case scenario. And we'll be looking at this 2 becquerel per liter guideline for cesium, because the other numbers are quite large. Again, we will be comparing to the IAE, ICRP suggested guidelines of 1 milligray per day for riparian animals or terrestrial animals. Okay, so now if you take the concentration in the river and compare it to these guidelines, if it equaled it, it would, if those two numbers equal, you form a ratio, of those, the concentration in your river compared to the concentration in the guideline. If that ratio equals 1, then you can discard it if it's 1 or below, and you assume that that radionuclide doesn't constitute a major risk. If it's above 1, then the probability exists that the concentrations were great enough to perhaps cause damage to the environment, so then you have to drop down into a tier 2 risk. So if we look at this, this is our 1 bar, and this suggests that cesium, cerium, and strontium-90 might have been released at rates that could have caused damage, that could have caused dose to these riparian animals of 1 milligray per day or greater. Remember that the similar graph that I showed you earlier had tritium being the highest concentration and cesium being relatively low. In this figure, where we're looking at relative effects, tritium is now at the very bottom and cesium has grown to the very top. This is because tritium is a beta emitter, and its potential contribution from a dose perspective is much less than the gamma emitting cesium-137. When you do a screen risk like I just conducted or showed you, and if certain things exceed that value of 1, then the next step is to be more realistic. The risk that I just showed you had very conservative numbers, trying to make a worst case scenario. For example, for this distribution coefficients, they used the value of 500 for cesium-137. That's a very conservative number. The real number, more realistic number on the Savannah River Site is 32,000, meaning that cesium attaches to the sediments much more readily and tenaciously than would be implied by this conservative analysis. So now I'm going to take the risk assessment one step further and use these realistic numbers rather than the conservative ones. When you do that, all the radionuclides drop out except cesium-137. So by this analysis, it shows that the reactors released the most radioactivity. They released it into rivers. The river that received the most was Still Creek. That animals, mammals particularly, that used that river system were subjected to a dose. That in certain years, in the early 60s and again in restart in the 80s, there's some probability that their dose exceeded 1 milligray per day, which is the IAEA guideline. However, not orders of magnitude above the 1 milligray per day. So there were probably effects to individuals, from what we know, but not to the population of animals. We can also look at maximum concentrations in other animals, like the deer that live there. And we can go into the literature and find out when concentrations were highest and what they were. So again, in the late 60s, there were deer that had 7,000 becquerels per kilogram. They would have to be concentrations 10 times greater than that to exceed the dose rate of 1 milligray per day. Occasionally, animals would go inside these seepage basins that I showed you. For example, turtles or various animals. This figure depicts that. So these are rather unique situations where animals became very contaminated. And this is several 100,000 becquerels per kilogram. The boxes show milligrays per day. So in some situations, the animals were getting 2 to 10 milligrays per day. But these are outliers and not typical. So, a summary of the radiological releases based on this rather quick analysis. There were indeed major radiological releases from the reactors, and they entered the streams. The largest doses were associated with animals that entered seepage basins. Those were the outliers that I just showed you. Some riparian animals received doses in excess of the IAEA guideline of 1 milligray per day. There is no evidence that dose rates were large enough to cause mortality. There are, however, lots of uncertainties in what I just did. There are considerable uncertainties about the releases and doses from short-lived radionuclides. This is because RAC, the organization that did the dose reconstruction, had difficulties defining the source term for short-lived radionuclides. Some important radionuclides were not in DOE's database when I did this. For example, phosphorus-32, a radionuclide with about a 2-week half-life, was not considered in this calculation and probably would have impacted dose as well as organisms. And finally, the calculations were based largely on annual release rates rather than averaged exposures. So that's probably not the best way to do this. However, having worked there for about 14 years, I'm pretty confident that the releases were not significant to to cause vast damage to the ecosystem. However, vast damage did occur. This is a depiction of one of those river systems, and you've got lots of dead trees, dead vegetation, and dead animals. So, if radionuclides didn't cause it, what did? The answer's here. It's thermal releases. Here's R reactor, and here is P reactor, and this is the temperature of the water that's being released. It's 70 degrees when it first comes out of the system. Even after going for some time through these canals and settling ponds, it's still very elevated. Here's 44 degrees. So thermal effects were major. This is the Savannah River, and the Savannah River Site is up here. These are the streams or rivers associated with each of the reactors. This is before any of the reactors started. This is the thermal impact from those reactors, with the dark color being severe and the white being no effect. And you can see that each of the rivers had severe impacts from the hot water that was coming from these reactors, particularly in this swamp system before it got to the Savannah River. There have been many, many studies on this. So the hot water effect decreased plant species. It decreased fish abundance and diversity. It increased parasite loads in fish. It impacted the aquatic insect communities. It decreased amphibian abundance and diversity. And it decreased the diversity of waterfowl. So it wasn't radionuclides in this case that had the environmental damage. It was the hot water coming from the reactors that caused major environmental impacts. The last thing I want to cover is change in land use. This is a satellite image of the Savannah River Site. This shows the rivers coming down to the swamp system and then the Savannah River. Notice that the Savannah River Site is this big green thumb surrounded by this mosaic pattern outside of it. This is because the mosaic pattern is villages, towns, McDonald's, cars, people living their lives. This area, the public was excluded. 20,000 people worked here, but they would drive in, they would drive out. No one was living there. And the reactors and such were in the central part. All this on the outside was a big buffer where trees were established and the public was kept out. There's a huge fence all the way around it. 50 years of keeping the public out had an impact also. It became a national environmental research park with species found in the Savannah River Site that are not found outside. So when we talk about environmental impact, we have a confounding variable. One could argue that this is actually good for the environment if you exclude humans. That same argument can be made for Chernobyl and possibly for Fukushima in the future. What's my time? Who's keeping time? Do I have time for one more slide? So I've showed you about releases and such, but I haven't showed you anything about the research that was done there. And there's a very rich radioecology research that came from Savannah River Site. There's the Savannah River Ecology Laboratory. It was founded by Eugene Odum. If you are an ecologist, you know the name of Odum. he is the father of ecology in the United States. And he started his work in radio ecology, but diversed into other areas. So let me just share one exciting data set with you that to me, if I had to name the top 5 slides in radio ecology, this would be one of them. What this is Pond B, which received effluents from that cracked reactor rod that I showed you a photograph. So this pond received all these effluents of cesium, strontium, and the transuranics. This is work from Dr. Ward Wicker. What he did was an inventory of all the radionuclides in this pond. By inventory, I mean he went and he caught fish and he measured the radioactivity in all the fish, in the fish species. But then he estimated the biomass of fish, and he made an inventory. Concentration times biomass equals inventory. He did that for sediments, he did it for insects, he did it for the aquatic plants. He then compared it, and the way to look at this is in this manner. All the radioactivity in this pond, 99% of it is cesium-137. Of that 1% that's remaining, 85% is strontium-90, sorry. Of that 15% that's remaining, you get into the transuranics. Another way to look at it is in this direction. Of all the cesium that's in that pond, 99% of it is tied up in the sediments. Of that 1%, it's divided between water and cestin, as well as the aquatic plants. Of that 1%, you get into zooplankton, fish, and benthic invertebrates. So the fraction of the total inventory that is in fish is very, very minor compared to the total inventory in the lake. And then you can compare those different percentages with the different types of isotopes. For example, strontium is more mobile, so rather than a lower percentage, 85%, is tied up in the sediments compared to cesium. What's also interesting is the mass of all these. So here he's taken the total activity. If we look at the specific activity of cesium, in other words, if we have 1 gram of cesium-137, its activity would be 3.2 times 10 to the 12th becquerels. So how does this number compare to the activity that he obtained? So this is the total activity in the sediments, 4.6 e to the 11th. All that activity equals 0.14 grams of cesium. A really tiny number mass-wise. If we look at the total in fish, 0.00001 gram. So the mass of these radionuclides is tiny, but the radioactivity can be very large and can be detectable in the entire ecosystem. Radioecology is a function of the isotopes, the function of the ecosystem that you're working in, and the function of the individual types of animals that you're studying. Thank you very much.
Hinton 先生、ありがとうございました。
はい、testimony.
それでは質問、コメントなどある方は挙手をお願いします。はい、お願いします。
どうもありがとうございます。リスクアセスメントのところで質問というか確認したいこと2つあるんですが、まず1つはそこに挙げられてた物質要素とかも書いてたんですけども、それぞれのリスクのアセスメントの評価は実際に観測したデータをベースにしたのか、それともその処理のプロセスのアクティビティに基づいて推計した値なのかというところが1つ。
It was based on average concentrations in the organisms.
実際に測定されたデータという、それと、銅図、その結果出されている銅図が、4.9 パーソンシーベルトってなってるんですけども、この施設に基づく銅図以外に背景バックグラウンドとして、この周囲の人たちはどのぐらい例えばラドンとかカリウムとかポータジウムとかそういうので暴露してると思うんですけど、それがどのぐらいなのかは教えてください。
So for humans, it was not measured. I said it was based on measurements, but that was for the ecological parameters. For humans, it was not measured. The dose calculations were based on releases and assumed intake parameters. The number that I showed you does not include background. That was the dose specifically from the radionuclides that came from the Savannah River Site. Background dose there, I don't know, I don't recall the exact number. It would be largely from cosmic radiation because there's not much granite or types of rocks that would contribute to the uranium, thorium progeny. Radon is not large there. Well, let's see, maybe I should back up. Radon is probably more than the cosmic radiation. I don't know those numbers. If you're truly interested, I could try to find those for you. I can say that background dose there, well, let's see. It's probably in the neighborhood of 2 millisieverts per year. The world average is 2.5 millisieverts per year. My guess is it's a little lower there, probably 2 millisieverts per year, per person.
ありがとうございます。他にありますでしょうか。はい、お願いします。
どうも、いろいろ面白いですね。で、ジールクリップのレシーブしたのなんですけれども、図を見ると、最大100デシベルパーセンターぐらいの濃度があるんですが、これ下流に下っていって、本線に乗り入れて、それが本線に流れていって、この居住地にそうですね、その時の濃度も、ある程度高い、例えばしてくれるパーツが、これはちょっとよくわかりませんが、そのあたりの濃度の敷地外の川の濃度で、そういうものはあって、そのあたりは公表されていたようなものでしょうか。
Thank you. So cesium was largely bound by sediments, as you know, and the releases went down those rivers into the swamp. And in the swamp, the flow of the water was greatly reduced and gave more time for cesium to bind to organic matter and sediment. It was a big trap for the cesium. That prevented much of the off-site dose. But nonetheless, you can, for many years, you could measure cesium in the water, you could measure cesium in fish downstream, you could measure cesium and tritium and many of the other radionuclides at the mouth of the Savannah River as it went into the ocean. I don't recall those numbers specifically. Dose calculations for all those people have been made and exist. Generally, the doses are maybe twice background or so as far as contributions from the Savannah River Site. This is like a PhD dissertation, all these questions. And the temperature's kind of warm up here too.
This is not a PhD dissertation. 先ほど生物の生死、モタリティにはほとんど影響が出てこなかったというおっしゃったんですが、遺伝的多様性についてはどうでしょうか。あるいは繁殖率、このサバナリバーのエリアの中で、例えば繁殖率が同じ動物でも変わってくるということがあったんでしょうか。これだけ長いリーケージが起こっているとその可能性があると思います。
Thank you. So the majority of these releases occurred in the mid-60s to early 70s, and we did not have the environmental ethic that we have now, and we definitely did not have an understanding of the environmental impacts, nor was there much interest in the environmental impacts. In fact, that's why they were allowed to discharge directly into the rivers. That would never be allowed today. So in some ways it's unfortunate, but the type of data that you just questioned wasn't examined during the peak periods of releases. People weren't out looking at fertility of fish or mortality of fish. Maybe mortality, because that would be very obvious if fish were floating. But as far as fertility, no one was looking at it, to my knowledge, and I've never seen those data. My guess, well, it would just be a guess. I don't know. It's probable that some impacts occurred, that some fish perhaps had a reduced fertility rate. I doubt if the reduction was large enough to impact the fish population, but it's a guess.
他にありますでしょうか。
大変有益なプレゼンテーションありがとうございました。鹿の体内中のセシウムの濃度で、占領率を計算されています。この場合、いわゆる内部被曝の計算になりますけれども、いわゆる生息環境の、外部被曝の占領は、小さいと見てよろしいんでしょうか。
I'm sorry, I missed the first part of your question. You're referring to humans or?
鹿の、体内中のセシウムの濃度で、占領率を計算されています。これは生息域における、外部被曝の量は、影響しないと見てよろしいですか。
The calculations included both internal and external, both pathways. Yeah. Did that answer your question? Did that answer your question? Yeah. Okay.
他にありますでしょうか。ありがとうございます。要素の
Oops.
あ、どうぞ。ごめん、もうちょっと説明。あ、どうぞどうぞ。Okay, after you. Okay. Let me talk.
In the back, please.
Yes. 要素131はこのこれだけ放出されていると動物の行動性の何が影響とかあったのかというのと、要素131はいつも放出されているものなんです。いつも検出されているもの。それだけ短い半減期の形がいつも検出されていたのかということがなぜこんなに出てしまったでしょうか。
Yeah. Let's see. It was released regularly. Let's see. I don't recall which facility released it the most. Let's take a look if we've got a moment. So it looks like most of the iodine-131 was released to the atmosphere and to the seepage basins. So the atmosphere releases would have been from the chemical separations facilities. They operated, in fact they're still operating, so they operated from the 1950s until, well, today. So that's the source term for iodine-131. There have not been many studies on iodine-131 at the Savannah River Site. I've not been there in about 10 years myself, but I understand that there are now some iodine-129 studies being done in which they hope to use that information to kind of back calculate what the effects might have been from iodine-131, but I've not seen the data published.
I have two questions for you. First of all, looking at the KE values, when you talk about conservative and realistic, when you say realistic, is that site specific?
Yes. Yes.
And the other one was half answered my last question. So what's the current status of the Savannah River Site? What's happening there?
So I'm not positive. I don't follow it very closely anymore. I'm more interested in Japan. But they have a huge waste problem. The United States has a huge waste problem. It's a political problem. So there is a lot of high-level waste stored on the Savannah River Site, and they have a vitrification facility where they take that waste and make it into glass rods. But there's been a lot of political yes and no's, do this, don't do this. So I don't know the status of that. That is their primary goal now, is a remediation and waste reduction purpose. They also started building a MOX facility, but I understand that that's now shut down because of cost overruns and delays. So I don't know what they're doing. Fortunately, they're not running any reactors.
もし説明もされてたら申し訳ないんですけど、栃木用区分のことでちょっと伺いたいです。栃木用の部分でそのサバンナサイト、リバーサイトのところでグリーンベルトっていう木々が周りを全体を覆ってて、放射性物質の拡散をちょっと防ぐような役割みたいな話を聞いたんですけど、これっていうのは核関連の施設ができる前からずっとそうだったのか、ずっとそうだったんですか？
Thank you. No, it was not in place. In the early 1950s, this was a very depressed area of the United States. It was agricultural based, small farms. The typical farmer had a mule. Do you know mule? It's like a horse that pulled a plow. So these were not affluent, economically affluent people. This was a depressed agricultural area. There was no national parks or thought of protection of the environment during this period. To the Department of Energy's credit, when they built these reactors and nuclear complex, they built this huge buffer area around it, in part for the very reason you just stated, to reduce the transport of radionuclides off-site. And it wasn't until the 1980s that this was declared a national environmental research park, and it was recognized at that time for the positive attributes of these endangered species that had become established on site.
います。他でよろしいですか？なければ、セッションを閉じたいと思います。ヒントン先生、ありがとうございます。それでは少し早いですが、休憩時間にしたいと思います。本田先生、休憩は予定通り取っていいですか、それとも早めに始めますか？早めに、
時間だけなんかですね。
はい、そうしましたら、ちょっと早めに休憩に入りますので、開始は10分にしましょう。3時10分、はい、から次の発表に入りたいと